So in chapter 1, we learned about continuity equation and we learned about Navier Stokes. So now we try to do the Navier Stokes equation so we could see what the dimensionless parameter that could have from the Navier Stokes equation. So we have, this is the very common Navier Stokes equation. We have rho d capital V over dt, rho g minus nabla p plus mu nabla square and v. So again, we need to list down the dimensionless parameter for all the parameter in this equation. So this is all the listing and this is the lambda, the nabla. So what we do is we substitute. So we have the d capital V here. So we substitute with the capital V. So it will become V star plus U. So and then we substitute all the dimensionless parameter here, and then we factorize the terms. So we get this one. So and then we could see, let's say we divide all the terms with a rho naught u square and L, and finally we will get this term. Okay, and then from this term, if we compare with the previous term like this one, so for example here, so we have rho star dv star over dt. So we found that it is similar with this one. And then we have rho g and minus nabla p. So here we have the rho and g. And then but we have an extra number here. So we have an extra terms here. So here we have the nabla p without any extra term, but here, for example, we have the mu nabla square v, so we have this term. And then we have an extra term here. So actually this is the term. So from this arrangement, we found that we also, in our research or in our works, that using this Navier Stokes equation, maybe it is worth for us to check or to use these extra terms to see the changes of that system. So the word of GL over U square is actually the Froude number. So actually in certain textbook, they will write Froude number is equal as V over square root GY. Okay. So this is the common Froude number in undergraduate textbooks. But now if you could see, this is a U square. So and then we have a G and L. And L here is actually the geometrical parameter, as I explained previously. But in this term, they use Y. So means the replacement between Y and L is actually can be considered because both are carries the geometrical effect. Okay, so means that from this one, so we could find that it's maybe the Froude number. So and then there are no extra terms here, and then we have mu rho u L over mu. Means, as I said, rho u L over mu is actually the Reynolds number. So and then means that if you want to do some things, maybe you could check the Reynolds number and Froude number. That's why sometimes if you read journal and so on and so forth, they will have a graph there. So they will change, they do a lot of experiment or simulation and so on. And sometimes they use the Reynolds number here, or they use the Froude number to evaluate the force, for example, the CD or CP and so on. So where they get the idea of Reynolds number or Froude number or what, any Nusselt number or whatever here. So it is because they are doing the dimensionless parameter according to the Navier Stokes. Okay, so this is very general Navier Stokes. So if you do your research, I propose you to solve the Navier Stokes first, because in your research, maybe you need to add something, or you need to, you have your own assumption, so you could simplify your Navier Stokes, then you could do the dimensionless process like this. If not, if you just use the common Navier Stokes here, so you will get these two terms only. Okay, so let's say we go for the two-dimensional Navier Stokes only for the x axis, because that one is the very general Navier Stokes. Let's say we focus on flow on the x direction. So I think you are familiar with this one. Okay, so and then we change the, normally the in Navier Stokes, the value of pressure is negative, because you know when water flow inside a pipe here. Okay, so maybe the velocity is remain the same, but for sure they are the difference of pressure. So normally we call this as a pressure drop. So because the velocity, the amount of pressure is reduced, so it going down. So means we put a negative in this term. So I explained this in the previous chapter. So this is the Navier Stokes for x-axis. So and then we do the same things. We recognize all the parameter, and then we have the dimensionless parameter like this, and we substitute all the terms into this Navier Stokes equation. Okay, so we have okay, so this is the problem is we have the value of this du over dy. So in the dimensionless parameter, we don't have the du dy. So we only have u star of equal u over u naught. So how we could get the value of du dx? So the idea is like this. So we assume that the u is equal to u star times u naught. And then if we have the du dx, so what we do, we substitute both these terms. So we replace the u with u star u naught and l star l naught, and then we factorize them, so we could get it is equal to u naught over l del u star over del x star. So this is the differential for these terms. So and then this is the differential for the pressure. So and then if you see this, we have the second derivation here. So and then it can be done like this one. So here there is some tricks to get this one. Okay, the idea of d del square u over del x square. So we could write like this one, and then we substitute the value of du dx that we get from the previous calculation here. Okay, so and then we substitute this one, and then we bring the okay, so the trick is like this. So we need to differentiate this one, d del over del x. So we just write del x star times del x star over del x. So means now we could cancel the value of del x here. So and then we rearrange this term into this one. So now we have del x star. So we have del u star over del x star, and then we have del x star over del x, and then we have the u naught over l. So and then so here in this one, I think from here we could know that we have the idea of x star over x over l. So and then for del x x star, so we could substitute the x star here as x over l. So and then we found that the del x is over del x, means we get the value of 1 over l. So it means that if you do the others, so we could have these terms. So we could substitute into this one, okay. So and then we could have this term. So and then means that from the simplification of this, so we could say that the del square u over del x square is equal to u naught over l square del square u star over del x star square. So we could do the same thing. So we could get the del square u over del y square is equal like this one. Now we could solve that equation. For example, we solve in a left-hand side first. So the left-hand side, it is like this one. So we substitute all the terms that we get from previous calculation. So we could get this one. So and then for the right-hand side, so this is the term for right-hand side. So we substitute all the terms. You could see here. So and then we could factorize it. So finally, we could have this equation. So then we just rewrite this in full terms. So left hand side is equal to right hand side. So we have like this one. So and then we could simplify by divide all the parameters with rho naught, u naught square and L. And finally we get this term. So and then for these terms we found that there is, if we compare with the previous, with the original, the 2D Navier Stokes equation for x-axis here, we found that there is only one extra parameter occur in this one. So we have the mu naught over rho naught, u naught and L. So mean this parameter is actually reflect the Reynolds number. So means that if you are only analyze flow on x-axis, okay, so means that the Reynolds number is the most important parameter because it's from the dimensionless analysis here, so we could determine the parameter of Reynolds number in these final terms.